All right, here we go. Unit 2, Day 2. This is going to be our second day introduction to derivatives. Today, the objective by the end of this lesson, you want to be able to estimate the value of a derivative at a function graphically at a point and understand the relationship between a graph of a function and a graph of its derivative, which we're going to see for the first time today. So first things first, when I say estimate the value of the derivative, what I'm talking about here is estimating, single most important sentence in all of calculus, estimating the slope of the tangent line. And so what we're going to do, just to refresh our concept of a derivative, we're going to take this function below and we're going to come up with the equation of tangent lines to that function at a few points. Let's start on the left here. We're going to go through for each of these. We're going to talk about the point of tangency, estimate the derivative, talk about whether the function's increasing or decreasing, and then come up with an equation of the tangent line. So at x equals -6, that's this point right here. This is the point -6, 0. We call this the point of tangency. You're going to see me abbreviate it POT. It's where is our function going to, or where is our tangent line going to just barely touch our function. To estimate the derivative, what I'm going to do is, as carefully as I can, I'm going to draw a dashed line to represent the line that would be tangent to this function, meaning just barely touching it once. It only has one point of tangency. It doesn't touch the function again locally. And so what we have here, that looks pretty good. And I can look at that red line and I can say, okay, that red line looks like it has a slope of 2/1. So it looks like an estimation. The derivative is the slope of the tangent line. The derivative at -6 looks like it's 2. And next couple of questions here, right? Is the function increasing, decreasing, or neither? One of the key points we're going to hit today is that if the derivative is positive, that means the tangent line at that point to your function has a positive slope, which means your function's on the way up. Our function is increasing at that point, increasing from left to right, right? Like this function is going up, so we say it is increasing. Finally, the equation of the tangent line, point-slope form. We have the point of tangency. We have the slope of the tangent line. If you have those two things, you can put a line in point-slope form. So again, point-slope form, we'll have y minus a y coordinate is the slope m times x minus an x coordinate. And so all we need to do here is plug this in. This is the easiest thing here when you have a point and a slope. We're going to say y minus the 0 from -6, 0 equals the slope of the tangent line, the derivative was 2, times x minus, in this case, minus -6. So we'll clean that up here. We'll say this is y equals 2 times x plus 6. And so that is the equation of this line tangent to our function at -6. The line y equals 2 times x minus 6. And so we're going to look through a couple more of these just to get the hang of it. At x equals -4, 1, 2, 3, 4, that's this point right here. I'm going to do that in blue, and I'm going to draw a tangent line here. Now this tangent line, right, this has a point of tangency at -4, +2. We have a flat horizontal line, change in y divided by change in x. There is no change in y ever to that blue line. It doesn't go up or down, so the estimation of this derivative, the slope of that tangent line, f prime of -4, is 0. And what we're going to find today is that when you have a function like that, anytime it hits its peak, anytime it hits a maximum, when it does that, it's going to have a tangent line that's horizontal. And so this function is neither. We're going to have here, and I'll add a detail, neither we are at a relative maximum. Meaning it doesn't have to be the maximum for the whole function, but just like around its local area, it is a maximum. And the equation of this tangent line, same thing, point-slope form, y minus 2 equals the slope of 0 times x minus -4 would be x plus 4. It's not going to matter though, because what we really end up having here, when we multiply by 0 and move the 2 to the other side, we're going to have y equals 2, which is of course the equation of that horizontal line when y is 2. And so second key point we're going to have here is at maxes and mins, at local maxes and mins, the slope of your tangent line is 0. the derivative will be 0. Just do 2 more here. When x equals -1, I'm going to go ahead and draw another. This one's going to be slightly less steep than the red one. This to me looks like, again, point of tangency -1, 1. Estimate the derivative. This looks like down 1 over 1. So f prime of -1 equals -1. The derivative is negative. And as you can see, our function is decreasing. It is on its way down. Our equation here of our tangent line would be y minus 1 equals y minus 1 is equal to -1 times x minus -1. That's going to be x plus 1. On the AP exam, you're done. You leave that in point slope form. No need to go any further. The last one I want you to see here real quick is that we have another place where our derivative is 0. Well, there's actually 2 more, but the only one we're going to look at here is when x is 1, our point of tangency is 1, looks like -4, 1, 2, 3, 4, 1, -4. If I were to draw this tangent line once again, that tangent line is the horizontal line with a slope of 0. F prime of 1 is also 0. We are neither increasing nor decreasing. We are at a relative minimum. And I can skip the whole point slope thing this form because I know how horizontal line works. That's the horizontal line, y equals -4. To summarize all of this, derivatives are positive when your function is increasing. They're negative when your function is decreasing because they match the slope of lines tangent to your curve at that point. And when you hit a relative min or max, your derivative will be 0. There are cases where derivatives do not exist. And so the way to really think about this first, we'll have like a formal definition later. But for right now, just think, can I come up with a tangent line? Because the derivative is the slope of the tangent line. No tangent line, no derivative. And so here are first 2 examples. If your function's at a discontinuity, done. There is no derivative at a discontinuity. So no derivative here. So f prime of 0 does not exist. F prime of 0 does not exist because we can't draw a line tangent to 2 different functions that are meeting, and have a jump discontinuity. On the right, if I were to try to draw a tangent line here, tangent means touch. So if we have a vertical asymptote, we never touch 3. F prime or -3. F prime of -3 does not exist or is undefined. That terminology is a little loose. You can use either one. F prime of 3 is undefined. It does not exist. So those are 2 cases. Here's another one. This is the one that's more interesting, right? The first one's just, okay, if I'm undefined, no derivative. The second one is a little bit trickier. But if you think about it in terms of the limit, like we did in lesson 1, it's actually not that bad. Remember, the derivative is the limit of the slope of the secant line. That was that graph where I kept having us, okay, calculate the slope between these 2 points, and now these 2 points, and now these 2 points, and now these 2 points. We didn't really get into it there, but in that case, it didn't matter whether I was coming from the left or from the right. They were the same. The slope was the same. The derivative will not exist if the slope from the left does not equal the slope from the right, or more accurately said, the limit as the change in x approaches 0. So if you have 2 different slopes at what we call a hard corner, you will not have a derivative. So this function will not have a derivative at f prime of 0. The derivative does not exist. Now I want to be clear here, you can have changing, right? As long as it's changing smooth, as long as there's no like abrupt hard corners. Like see here, you're going to have, on this one, you're going to have an abrupt hard corner. These are approaching, one, the slope is going to -infinity, the other to positive infinity. So hard corners, also no derivative. Finally, the last one here, at a vertical tangent line. So this one, also once you kind of think about it in tangent lines, it's not bad. If I look for what is f prime of 0 here, and I try and draw this tangent line, my tangent line touches right there, and it is a tangent line, but its slope, change in y over change in x, That's a vertical line. It has no slope. The change in y over change in x is undefined, so f prime of 0 here does not exist. So those are the cases where derivatives do not exist. Last portion for today, we're going to talk about analyzing graphs of functions and analyzing graphs of their derivatives. And so this is so key here, is paying attention. Do I have a graph of a derivative or do I have a graph of an original function? And what I have here in red is an original function. In purple is the derivative of that function. It is the derivative, meaning if you took the derivative, if you found the slope of this line and slope of this line and this line and this line, if you found the derivative at every single point of this function and you plotted those derivatives, that's what the graph is in purple. Just like two quick examples so you believe me. At -1, horizontal tangent line, derivative is 0. At +1, horizontal tangent line, derivative is 0. Here are a couple of other really important ones. Notice f of x is increasing on 0 to 1. What I mean by that is from 0 to 1, this graph is on its way up. On the purple graph, yes, the derivative is on its way down, but it's still positive. It's still above 0. It's positive, it's positive, it's positive. The derivative, because it's the slope of the tangent line of that function, is positive. And then if you look at next, then this function is decreasing all the way to 1. Well, check this out. The derivative is decreasing from -1, sorry, not is decreasing, is negative from -1 to +1. And then finally, when this function starts heading back up, what colors do I have left? I have gold left. When this function starts increasing again, our derivative is positive. So the key points here, taking this all in at once, if the derivative is above 0, if the derivative is positive, that's blue and gold, my original function is increasing. If the derivative is below 0, that's in green, those negative signs, the original function is decreasing. Two more to notice here. We have a relative maximum at -1. We have a relative maximum whenever our derivative goes from positive to negative, whenever it crosses the x-axis. We have a relative minimum whenever our derivative goes from negative to positive, whenever the slope of the tangent line goes from negative to 0 to positive, versus at maximum, the slope of those tangent lines go positive to 0 to negative. And so these are all, make sure you carefully look over this printed note sheet. All right. So real quick, two last things. I think I'm going to make it here under like 18 minutes. Analyzing f of x graphs versus f prime graphs. The key point here, pay very close attention to what you're given. So the most important thing, it says here, the graph of a function g of x. The first thing I do is I label that function g of x. So I know I'm talking about a function, not a graph of its derivative. The intervals where g prime of x, where the derivative is less than 0. Okay, the derivative is less than 0. That means g of x is decreasing. So where is g of x decreasing? Well, it's decreasing from 3 to -2. Or sorry, I was reading the y values there. That's my bad. From 4 to -2. -4 to -2. And from 1 to infinity. From 1 to infinity. Where are the intervals where g prime is greater than 0? If g prime is greater than 0, g of x is increasing. If the derivative is above 0, the tangent line slopes are above 0, my function is increasing. So that's from negative infinity, I mean left, not down, from negative infinity to -4. This should be kind of the inverse of what are these above, right? It's like this, then purple takes over, then increasing is going to take over again from -3 to 1 here. And so altogether that represents my entire function. Now where is the derivative 0? The derivative is 0 at max or min, at a relative max or min, because that's going to be where I have horizontal tangent lines. And that's going to be at -4 and +1. Functions increasing, derivatives positive. Functions decreasing, derivatives negative. Now where this is slightly trickier is if you are given a graph of the derivative. And you have to be really careful just to notice when that is happening. So this is hard mode, when you're given a graph of the function's derivative. The first thing I do when I read one of these problems, I see that and I said, okay, I'm given a graph of the derivative. I write that right here just to make sure I know that this is the derivative of h of x. This is not a graph of h of x. I repeat, this is not a graph of h of x. It is a graph of its derivative. But I'm being asked questions about h of x. H of x, I have no idea what that looks like. But the derivative tells me a few things. Where is h of x increasing? If h of x is increasing, h prime of x is positive. H prime of x is greater than 0. So that's going to happen from -2 to 1. And it's also going to happen from 3 to infinity. Again, infinity there means to the right. It happens to be going up, but that means to the right. Those are the sets of points where h prime is above 0, is above all positive means, is above the x-axis. That means my h of x function that I can't see is increasing. Where is h of x decreasing? Well, it's decreasing when h prime of x is less than 0. So it's decreasing on this blue, which is from -infinity to -2, and then on this bottom portion from 1 to 3, because those are the sections where h prime of x is negative, is below. So again, you got to remember, this is negative below, this is positive above. And negative positive tells us h of x increasing, and negative tells us the original function decreasing. All right, where does h of x have a relative maximum? A relative maximum happens if you go from a positive slope to a 0 slope to a negative slope, right? If your tangent line was positive, hits 0, and then becomes negative, that means you were at a maximum in your original function. And so where that happens on this derivative graph, where does our derivative, where was it positive and then becomes negative? At x equals 1. Our derivative was positive and becomes negative. The slope of the tangent line was positive, is 0, now is negative. That's a maximum. What about a minimum, right? Where is our function going to have a relative minimum? Well, that's going to be where we go from negative down to 0 to positive. A negative derivative, a 0 derivative, and then a positive derivative. So where is that going to happen? Turns out that's going to happen at -2 and looks like 3 there. At x equals -2 and x equals 3. Finally, last one. If h, we're not going to do this last one down here, but if h of -1 was 1/2, what is the equation of the tangent line drawn to the graph of h of x at x equals -1? Again, we don't have h of x, but if you can find a point in a slope, you can draw a tangent line. We have a point. They gave it to us. They gave us the point of tangency is at -1, 1/2. So I can already fill in part of this. Y minus 1/2 equals some slope times x plus 1 minus -1. All I need now is I need a slope of the tangent line. The slope of the tangent line, single most important sentence in calculus, is the derivative. So what is the derivative at -1? F prime of -1 equals 5. The derivative of our function at -1 is 5. The slope of our tangent line at -1 is 5. That is how you would make the equation of the line tangent to h of x at that point.